Come on, how do we get rid of the... Nope, that wasn't it. Well, that was sort of it. Okay. Anyway, we talked about how the right orientation in general is to have the largest group on your stereo center. Suddenly, it's not wanting to recognize the Apple Pencil, which is weird. Sorry, guys. Anyway, the appropriate orientation is to have the large group perpendicular on the alpha carbon to the carbonyl group, to be 180 degrees away from the trajectory of the nucleophile, to minimize steric problems, also to promote sigma to sigma star hyperconjugation between the nascent being born, newly forming sigma star between nucleophile and carbonyl, and then the sigma bond on the adjacent carbon between the alpha carbon and the large group. Then you've got two different diastereotopic faces that you can attack that conformation from. From the one on the left, the nucleophile approaches via the Bürgi-Dunitz angle eclipsed with the small group. For the one over here on the, my other left, this is the right side, sorry, over here on the left-hand side approach, the nucleophile will be eclipsed with the medium group. That's more sterically hindered, so this approach is favorable, and in that way, the stereochemistry at the alpha carbon controls the configuration of the newly formed stereo center at the carbonyl carbon. All right. So we talked about a variation of that where you have on the alpha carbon electronegative heteroatom, where now the sigma star associated with this carbon-nitrogen bond should be low, and that's the dominant effect. Again, though, the nitrogen is going to be opposite to the incoming nucleophile, again because of sterics, and also to promote hyperconjugation, not this time between the newly forming sigma bonding orbital between carbonyl carbon and nucleophile, and then the sigma star drawn in the back between the alpha carbon and the nitrogen. Okay, any questions about that? Yeah.
Did you click record?
I did click record. Yep, now I got to get rid of the square of doom again. I think we did it. All right. Yeah. Okay, then we're using similar types of considerations to talk about addition to cyclic ketones. There's a couple of issues to deal with here. One is the observation that cyclic ketones react 300 times faster in lithium aluminum hydride reductions than their acyclic counterparts. Part of this is relief of torsional strain. In the cyclic ketone, those equatorial alpha protons are basically eclipsed with the carbonyl group, and therefore when addition happens, you relieve that pseudo-eclipsed interaction, which ends up being worse and less favorable than any of the 1,3 diaxial interactions that you introduce. And so that's one of the reasons why the ketone reacts faster. Now, it wasn't obvious actually from this ketone because the two faces of this ketone are identical. But if we have this T-butyl substituted ketone, we now have two diastereotopic faces of this ketone. We were talking about which addition from which of them was preferred. We analyzed a couple of different things. We sort of drew out the Bürgi-Dunitz trajectory here, 105 degrees with respect to the plane of the carbon-oxygen pi bond. We noted that approach from the top face sort of brings you in contact with these axial beta protons, whereas approach from the bottom face sort of brings you in contact with these axial alpha protons. We noted that approach from the bottom face maybe gives you steric problems with respect to that T-butyl group, though you're still kind of far away, so it's unclear what difference that would necessarily make. But at the end, you guys made me tell you I was going to make you wait until today, but told you that the observed ratio is 9:1 for addition of the proton on the top face versus the bottom face, okay? And I told you it had nothing to do with product stability. Why is that true? Why does it have nothing to do with product stability? It's an irreversible reaction. Never use product stability to explain the outcome of an irreversible reaction. Unless No, I can't think of a time where you would do that. Even the Hammond postulate doesn't get you out of that situation. Okay. So let's deal with why we see that addition of the proton on the top face is more favorable. Couple of different considerations, sterics and electronics, naturally. So let's look at the transition state for addition of a hydride equivalent from the top face. I'm just going to draw the 6-membered ring, and I'm going to draw the oxygen here. The hydrogen is coming in here, being delivered there. Pi bond is breaking. At the same time, a bond between aluminum and hydrogen is breaking because we're delivering the hydride. Oh, what is that? I don't even know what that is. Transition state, double dagger. I'm going to put those axial beta protons here, alpha, beta. And then I'm also going to draw at least on this side the alpha protons, okay? And you've got axial versus equatorial alpha protons. So in this transition state from the upper face, the top face of the molecule, let's sort of look into the types of steric problems that are being introduced. And stinking notability, it doesn't like to let me shrink and move at the same time. Okay, so as we go from starting material to transition state, we are, as I mentioned above, we are relieving this pseudo-eclipsed interaction between the carbonyl group and the equatorial alpha proton. Instead, now what we're getting is developing gauche interactions between the alpha protons and the negatively charged oxygen. Okay? So that should be favorable, right? We're getting rid of an eclipsed interaction. We're replacing it with some kind of gauche interaction, which is probably the best you can do. And then the other thing we're doing is we're introducing a 1,3 diaxial interaction, but it's between beta protons and our new incoming, hydride proton, which I'm just going to label orange. Okay? It's a 1,3 diaxial interaction, but it's probably the least bad of the options, right? Because it's hydrogen. And we have a sense for how bad 1,3 diaxial interactions are. They're called A values that we got from our chapter on conformations. All right, so that's the transition state that leads to the major product. Now let's look at the alternative transition state and see if we can rationalize why it might be higher in energy. So again, let's see, we're going to draw. In this case, the oxygen would be going axial. The hydride would be delivered here. Here's my alpha protons that are axial and, no, that's not axial, silly. Equatorial and axial protons, and then here's my beta protons. Okay, So what have I got going on here? Well, I have a developing diaxial interaction with the negatively charged oxygen and the beta protons. And then here I'm getting just sort of a gauche interaction between alpha protons and my incoming hydride. Oops. All right. Anything else going on that that we haven't noted there? Steric problems, any difference between any in the interactions associated with this?
Yeah, well, I mean, that like OH13 direction is less favorable.
Right. Okay. So the question is comparing these two, how much worse is it? Some, a lot-ish. We actually have a number for that, and that came from chapter 3, I think, on conformations, or was that chapter 2? We've got a table of A values somewhere that I'm going to look up if I can find them. Non-classical carbocations. Aren't you glad we're not doing that? Okay, so I'm looking up the A value for oxygen. I don't know whether it should be OH or perhaps something slightly bigger than OH because it's maybe got a lithium chelated to it. So let's just go ahead with the A value for OH is around 1 kilocalorie per mole. Okay? So it would be a reasonable estimate to suggest that this transition state over here, is perhaps as much as a kcal per mole higher in energy than this transition state here. Now, what magic number equals 10? 1.3, 1.4, yeah, 1.36. Way to go on your significant figures, folks. Sometimes I think I have no business knowing anything to the hundredths place, but anyway, right, 1.36 is a factor of 10. So we've got a almost 10, a little bit less than 10 preference for this transition state over that transition state. That's pretty consistent with a difference in free energy between the two transition states being around a kilocalorie per mole and being because of this steric reason. There's an alternative explanation, though, that has to do with electronics and likely contributes as well. But before we move on there, anything you want to ask about the steric issue? Yeah.
Okay, wait, so I might just be missing something. There's the gauche interactions, like on the first one there's gauche between the alpha hydrogen and the oxygen.
Okay.
But shouldn't there also be gauche, like, aren't there gauche interactions with the oxygen either way? It's just with different hydrogens?
That's right. Yeah. So the major thing that's changing is probably these 1,3 diaxial interactions.
Okay, so there's not like...
That's why I didn't necessarily compare those. Right, here this oxygen is gauche to 2 hydrogens. Here the oxygen is gauche to 1 hydrogen and gauche to the ring. That kind of difference, though, is probably also tied up in the A value, because remember, the A value is actually related to the equilibrium constant for that. I just can't stand that. That's terrible. I also can't stand that. There we go. That's better. Up stays up and down stays down. The A value comes from this equilibrium constant issue, right, where we're dealing with, I think the A value takes into account the differences in the gauche interactions in addition to the 1,3 diaxial interactions. Yeah. Okay. So let's deal with the potential electronic explanation. It's probably both of these. The electronic explanation sort of relates to what we talked about before with the Falcon-On model. It's called more broadly the C-plaque effect for the PI that sort of came up with the idea. And it relies on the idea of a low energy carbon nucleophile sigma star that is early on in the transition state. And a preferred arrangement, or the preferred pathway, the preferred approach, is for the nucleophile to approach anti to the best donor sigma bond. In other words, we're looking for sigma on the adjacent alpha carbon to sigma star carbon nucleophile nascent newly forming sigma star as we saw before as we were thinking about the Falcon-On model, right? Do you remember we talked about the nucleophile approaching anti to this donating group? We're going to do that here as well. So let's look at those two transition states that I drew above. I'm going to try to copy. There's so much going on, but maybe I can copy that. And let's consider what's on the alpha carbons as the nucleophile approaches. Okay, so I'm going to draw the nascent carbon hydrogen sigma star as this new bond is being formed. Okay, that's going to look like, and it's low in energy because the bond is weak, only just being formed. That would look something like this, with a large lobe going towards the bottom face of our molecule. In the course evaluation for this class, if you want to say something like wastes too much class time coloring, I feel like that would be useful feedback for our department chairs to help me improve. So feel free to put that down. Along with any other legitimate questions or concerns you might have. We do read them, and they're asleep at the computer. Guess I should bring a plug to. All right, we're still recording though. That's nice. Okay, on the adjacent, but somehow the iPad doesn't want to work now. That's weird. Okay, we're back. All right, so there's the nascent sigma star. If it approaches anti to those axial protons, then the adjacent carbon-hydrogen sigma bonding orbitals can line up with, excuse me, and donate into that nascent sigma star and stabilize it. So you've got approach with axial approach anti to those alpha protons provides good hyperconjugation. Of course, this wouldn't be complete if we didn't also try to do the same thing for the other transition states. So let me just draw close enough. Copy. Zoom in. Let's try to draw where the carbon hydrogen sigma star would be on that hydrogen, a little bit here, and then sort of jutting out into the back. And I think the idea is that as arranged like this, there's not necessarily as good of overlap. I think you could argue that there's overlap with the alpha to beta carbon-carbon bonds. And so the argument would have to be that the carbon-hydrogen bonds are better donors than carbon-carbon bonds. I don't know that I can justify that to you.
Is it kind of the same idea that they're, like, when we talked about similar electronegativities?
Yes, it likely involves that. Carbon-hydrogen bonds are pretty strong, just because hydrogen is small, and so they're short, and short bonds are strong. If you look up homolytic bond cleaving energies for carbon-hydrogen bonds versus carbon-carbon bonds, there may be 20 kilocalories per mole different. I don't know how to tell you whether carbon-carbon bonds are higher or lower than carbon-hydrogen bonds. So I'm not totally sure how to justify that. And I looked in your text, and they don't necessarily have a great explanation for that as well. Because I mean, as you look at that, I'm like, well, okay, but it sort of aligns fine with those bonds, right? And the argument is the overlap is better here. But I do wish I had a better answer for you on that. Okay. Yes?
So this model is saying that, or like the
C-plaque effect, yeah.
It's saying that like the better donor is going to direct the.
The best, the most electron-rich bond should be anti to the approaching nucleophile. To best facilitate sigma to nascent sigma star hyperconjugation.
Give us another example. Is it okay if you don't?
Do I have another example?
Or should I just like Google C-plaque effect? Sign my computer out.
You can probably do it faster than I can.
So they approach anti to the best donor signal.
Yep, approach anti to the best.
I found a Wikipedia example.
I did too. Huh. So we're probably looking at the same page.
Probably. Is it, I think it's called lower form, but I might be wrong about what it is.
No, this isn't. I mean, we could do that example. Sorry. This is again a lithium aluminum hydride reduction. Blah. So we're looking at equatorial delivery of hydride versus axial delivery of hydride. With the methyl group, it's 95% axial delivery versus 5% equatorial delivery. And we're talking about R here is either methoxy or methyl. It's one of those alpha axial substituents. And then if it's methoxy, the ratio is 87 to 13.
Why?
Not a huge change, but the idea is that the carbon-carbon bond is a better donor than a carbon-oxygen sigma bond because oxygen's more electronegative than carbon, meaning carbon-oxygen bonds are lower in energy than carbon-carbon bonds.
So wait, which way did it approach from? Was it from the top?
The hydride
It was anti to the
best approach in both cases is from above because of the steric issues that we talked about, but you can tune the extent based on the identity of this R group. Yeah.
I think the helpful one.
Okay. And I think there's a lot more examples. The Wikipedia article, as always, has a criticisms section. I feel like that sort of describes, if my life is summed up at some point in a Wikipedia article, there's going to be bio, history, prose, criticisms. Yeah. Could have done better at that. All right. Lastly, and this is just kind of fun, if you switch to a set of conditions for hydride reduction of carbonyls, switch to equilibrating conditions, then you do not worry about transition states at all. The only thing that matters is product stability. So the following is called the, you don't want to know this, nor do I want to write it, but I'm going to write it anyway. Meerwein-Pondorf-Verley reduction.
I think that's where my last name comes from.
Really?
Yeah, like Worley, like barely.
Verley, okay.
What in the Tolkien?
What? And this is a weird reaction that involves aluminum triisopropoxide, and it's in equilibrium with acetone and the following two isopropoxides. One has the hydride delivered from the top, and then the other, has the hydride delivered from the bottom, so that the oxygen group is axial. And this is an equilibrium process. If you've not seen this reaction before, it's really not actually that bad. I'll draw just a bit of the arrow pushing mechanism for you so you have an idea of what's going on. Likely the oxygen of the ketone engages in a Lewis acid, Lewis base complex with aluminum. And then one of the isopropoxide groups sort of leans over, and you get a concerted reaction where these electrons form the carbonyl. We deliver the hydride there, and then we make a full covalent bond with aluminum. That's an equilibrium process, and the process is governed entirely by the stability of the products, which is 95% axial delivery of hydrogen and 5% equatorial delivery of hydrogen. That's greater than a 10-to-1 ratio, which tells you that the A value of the aluminum group is probably higher than for just OH on its own. And you could probably even calculate that based on that product distribution. Okay, so that's some stuff about addition to carbonyls. Want to take just a minute to talk about conjugate addition reactions. Your text calls this nucleophilic addition to olefins, but I'm just going to call it conjugate addition. You've encountered this before. You can think of this as nucleophilic addition to an alkene or an olefin, where one of the groups on the alkene is an electron withdrawing group. Sometimes this is also called 1,4 addition for reasons we'll mention briefly. Sometimes if the nucleophile is an enolate or a carbanion, we'll call it a Michael addition. I've never heard it called bimolecular nucleophilic addition, or ADN2, but your text uses that. I'm not going to write it down because I don't care. All right, so an example of conjugate addition would be an alpha beta unsaturated carbonyl group. And that's your electrophile. Then you have a nucleophile, which can be any number of things. I'm choosing a thiolate on purpose. We'll have to say something about 1,4 versus 1,2 addition reactions. The standard mechanism is we attack the beta carbon. It's useful if you've got some MO theory intuition and recognize that as a conjugated system. The LUMO there should be not just the pi star, right? The HOMO and the LUMO of this molecule. Well, fine, let's just do that. What would you say the HOMO of this molecule is?
Split between the alpha and the C, or the carbonyl, like an orbital on.
Okay, you are right that there is a delocalized filled pi system involving orbital density on each of these atoms, but that's not the HOMO. HOMO is actually one of the two lone pairs. There should be an S-rich lone pair and a P-rich lone pair, and the P-rich lone pair is probably the highest energy one, okay? So the HOMO of this molecule, alpha beta unsaturated carbonyl compound, is probably lone pair on oxygen. How about the LUMO? One of the pi orbitals. When we have conjugated atoms, 4 of them lined up together, we sort of drop the pi and the pi star. I'll just, you can do this through a group orbital approach, or just think here's beta carbon, here's alpha carbon, carbonyl carbon, and oxygen. I'm drawing the view looking down on this pi system with p orbitals all aligned together. One of them has them all together with the same wave function sign. Another would have a node in the middle. Does that look sort of familiar?
Mm-hmm.
It's kind of like 1,3-butadiene orbitals. Nodes here. And then the highest energy option would look like this. If we think about the electrons, I'm angry with myself because I didn't draw them in order of energy. And now, there we go. Sorry. Move that up, move those down. And, whoa! I just about dented my computer with my water bottle. That was scary. All right, and we've got 2 sets of electrons shown in the Lewis structure in the pi bond between the alpha and the beta carbon, the carbonyl carbon, and the oxygen. So we would fill these 2 lower energy pi orbitals. The higher 2 would be empty. This is going to be the LUMO of the molecule. So the LUMO is one of these delocalized pi orbitals. The important point is that it is on the beta carbon in addition to the carbonyl carbon. When we look at carbonyls, we're used to thinking, okay, the LUMO is the pi star, but you got to watch for conjugation. If it's conjugated, that LUMO is spread out. The other issue going on here is that unlike 1,3-butadiene, where the 2 double bonds on either end are the same, here you've got an electronegative oxygen. Okay, that means conceptually I could build these pi molecular orbitals from mixing of the carbon-oxygen pi bond with the alpha-beta carbon pi bond. The carbon-oxygen pi bond's lower in energy. So what that tells you is that the bonding orbitals are going to be biased towards oxygen, and the anti-bonding orbitals are going to be biased towards the beta carbon. And we can actually show this in Spartan. Oh look, you remember cyclopropane? That was a long time ago. Here's just that carbonyl compound. I'm going to see if it's got it in the database. Behold, it does. Look at that. The HOMO is a p-rich lone pair on the oxygen. The LUMO, as you can see, has a pretty large coefficient on that beta carbon. Whereas the lower energy pi orbital is, ignore this portion, that's a pi CH2 actually interacting with the extended pi system. Think about group orbitals. But this looks like this lowest energy orbital that I drew here, but it's leaning towards the oxygen, and that's because of oxygen's electronegativity. Later. No. All right. So the point is that in those pi orbitals, the bonding orbitals are biased towards oxygen. The empty LUMO anti-bonding orbital is biased towards the beta carbon that's right here. All right. So all of that's just to say that a nucleophile approaching an alpha-beta unsaturated carbonyl compound has a choice as to where it's going to attack. That LUMO is on both the beta carbon and the carbonyl carbon, though as I showed you, the orbital coefficient's a little bit higher on the beta carbon. That thiol will preferentially attack the beta carbon. Then as we push arrows, we actually show the bond between alpha and beta carbon breaking to form a new alpha to carbonyl carbon pi bond, and then the carbon oxygen pi bond breaking and going out onto the oxygen. It's thought that that is the rate determining step. Here is the new bond between thiol and the between thiol and the beta carbon of my alpha beta unsaturated pi system. Here is the enolate product that I make as a result of this attack. And then our standard arrow pushing will show enolate getting protonated on the alpha carbon, usually by some kind of solvent. And then the product of this reaction is your nucleophile is now attached to what was your beta carbon. Carbonyl carbon, alpha carbon, beta carbon. Okay, does that look familiar? You've seen that maybe before. Okay, now you might have heard of this as a 1,4 addition, but if you're paying attention to the things that we added, you can see where the 4 came from, but it's unclear where the 1 came from, and we're going to clear that up here, right? Because the two things we added were the nucleophile and then the hydrogen. And if we start counting at oxygen, why do they call that a 1,4 addition instead of a 3,4 addition, or perhaps even just a 1,2 addition, because the things that got added are next to each other? Here's the answer. This protonation by solvent on the alpha carbon was an oversimplification. I'm going to draw the general intermediate where the nucleophile has made a new bond to, the beta carbon. And you end up with this enolate intermediate. It's actually been known for a long time that even though the negative charge is delocalized on both the alpha carbon and the oxygen, that protonation rates for enolates are not equal on the oxygen and on the alpha carbon. It turns out that protonation is faster on heteroatoms. So the thing that happens first is that your hydrogen gets delivered to the oxygen of the enolate, which, if you're following along, gives you this enol. But the enol is the less stable tautomer, and so you get slower tautomerization to the more stable keto form, where that proton ends up on the alpha carbon. And something's horribly wrong here. No? It wasn't horribly wrong, but now it is. So tautomerization would presumably involve either addition of a proton to the pi bond followed by removal of the proton from the oxygen, or deprotonating the oxygen first and then adding the proton on the alpha carbon. And the idea is that that's the keto form is more stable. Why is that? Why is the keto form more stable than the enol form?
Proton's more acidic in the enol form.
Okay, proton's more acidic in the enol form than the keto form. Okay, I hadn't thought about that, but that's certainly true. I mean, I don't know. We'd have to pKa for protons, alpha to ketones. You're looking at around 20. pKa for an enol oxygen. I actually don't know what that number is. We can look it up.
Alcohol is 16.
For alcohol, it should be 16, but for a resonance stabilized, it may be less than 16. Okay, strongest acid loses its proton. That maybe makes some sense. Probably less than 16. I don't know what to guess. There's other issues here, and that's comparing bond stability. So over here, you have an oxygen-hydrogen sigma bond, a carbon-carbon pi bond. Over here, you have a carbon-hydrogen sigma bond, and a carbon-oxygen pi bond. It turns out the major effect is that the carbon-oxygen pi bond is quite a bit more stable than the carbon-carbon pi bond. Again, owing to oxygen's electronegativity. It's true that an oxygen-hydrogen bond is more stable than a carbon-hydrogen bond, at least in terms of bond dissociation enthalpies, but the difference isn't huge. So, and you can look up, we could look up bond dissociation enthalpies, but if an OH bond is like 105 kilocalories per mole and a carbon-hydrogen bond is about 100 kilocalories per mole, that's a 5 kcal per mole difference. What I'm saying is the difference in stability between carbon-carbon pi versus carbon-hydrogen pi totally and overwhelms and makes up for that difference. Okay, so that's where the 1,4 comes from. You can see that if we protonate on the oxygen, the things that got added, at least at that intermediate stage, here's your nucleophile, here's your hydrogen. When I teach this in an introductory OChem class, though, I don't bother because that's a lot of words for not a lot of payoff, at least in terms of how do I predict this product. So yeah, the final product that you give here is shown correctly, but the reason we call it a 1,4 addition is because the first thing you form is the enol. Let's say just a little bit in the last minute or two about 1,2 addition versus 1,4 addition. 1,4 addition is conjugate addition. 1,2 addition is where a nucleophile attacks at the carbonyl carbon. So we should talk about what makes one preferred over the other. In the introductory OChem course, you may be memorized cuprates attack at the beta carbon. And then organolithiums and Grignards attack at the carbonyl carbon. That actually correlates pretty well with hard-soft acid-base theory. That is, harder nucleophiles tend to attack at the carbonyl carbon. Softer nucleophiles tend to attack at the beta carbon. The reason harder nucleophiles attack at the carbonyl carbon is because things like organolithiums and Grignard reagents have counter ions that often chelate and coordinate that oxygen, and so it makes sense they're going to be close anyway. Okay, for softer nucleophiles, electrostatics are much less of a big deal. Softer nucleophiles like thiols or cuprates, there the thing that matters most is where is the LUMO, and it's mostly, the LUMO coefficient's mostly on the beta carbon. So you'll see in general that softer nucleophiles like thiols, cuprates, amines, enolates attack the beta carbon. Harder nucleophiles like organolithiums or grignards will attack the carbonyl carbon. And that's a little bit more satisfying than having to memorize it. Not much, but a little bit more. Okay, we will end there. Have a very happy weekend.